So let's do an example. We're going to construct a confidence interval. A machine that fills cereal boxes is supposed to put 20 ounces of cereal in each box. A simple random sample of 6 boxes is found to contain a sample mean of 20.25 ounces of cereal. It's known from past experience that the fill weights are normally distributed with a standard deviation of 0.2 ounces. So it's from a normal distribution. So I can use the central limit theorem when calculating my margin of error. To get the margin of error, I need to know, hey, what's the critical value for 90% confidence? And then I multiply that by the standard error, which is the population standard deviation that I have, and my sample size is 6. So how do I get my critical value for a 90% confidence interval? I check my A3, my pink table. I go to the bottom. Is 90% confidence there? Yes. So my critical Z value is 1.645. So my critical Z value times standard deviation divided by the square root of my sample size was 6 boxes. I'm rounding that to 3 decimal places. That is my margin of error. So what I'm going to do is I'm going to take my sample mean, which was given to me, and I'm going to add and subtract my margin of error. That's how I get my interval. I don't have the population mean, that's mu. So I'm going to take my sample mean and add and subtract the margin of error. So my sample mean was 20.25 minus my margin of error we calculated. And then I'm going to add that. Minus 0.134. Alright, so for this lower value, I'm going to round it to 2 decimal places because that's what the sample mean went out to. 20.25 plus the margin of error. I'll go to 0.38. So we are 90% confidence that the true population mean of the weight of cereals in each box is between 20.12 and 20.38. This is my interval or my window that we believe that the true population mean falls in between. The other type of example in 8.1 is when we're actually looking for a sample size needed to get a certain margin of error. So you can make a margin of error smaller if you're either willing to reduce the level of confidence, or you can make your sample size larger. By increasing your sample size, you're making this more accurate, so your margin of error will be smaller. So if you rewrite the margin of error formula and solve for n, it looks like this. This is the formula we're going to use to say, hey, how large of a sample size will I need to fit these expectations? Let's do an example. So if a scientist wants to estimate the mean weight of mice after they've been fed a special diet, from previous studies, it's known that the weight, we have a normal distribution, and we have a population standard deviation of 3 grams. How many mice we're solving for the number or the sample size needed for a 95% confidence level, and I want to keep my margin of error to 0.5. So I'm solving for n. So I need a critical z value for 95% confidence. This comes from my table, my pink cheat strip on the bottom of A3, 1.960. The margin of error, M, and this is how I use same notation, different notation, it's both margin of error, will be 0.05. I've got my critical z, I know my population standard deviation. So 1.960 times 3, enter, divided by 0.5, enter. Now don't forget to square this, gets rid of that square root we had. So my number is 138.2976. We're talking about mice here. We can't have a fraction of a mice. We have to round up to the next whole mouse. Can't cut a mouse in half and have it be useful. So we're rounding up because this is a sample size of an item. So 139 mice.